All right, welcome everyone to this month's GITA webinar on how accurate is your drone. We have Mike Tully and Ben Houston on to give us a little more information about drones and drone data accuracy. We'll get into introducing them in a second, but first I'd like to make a couple announcements for GITA.org. Again, on behalf of everyone at GITA, thank you all so much for participating in these webinars. I think these provide great value back to the organization. And if you have any comments or can think of ways or content that we need to be presenting through these webinars, please reach out to me directly and let me know. My email is president-e, which is president-elect, so president-e@GITA.org, and that'll get you to me. I want to announce that we have our Pipeline Technology Forum coming up October 16th and 17th in Houston. That is a great event. It's been going on for about 27 years, so we're very excited to extend that. We're also looking for scholarship opportunities. If yourself as a student or you know someone that's a student that's looking for a scholarship and they're studying GIS in college, point them to the GITA website and have them fill out the scholarship information. We are also looking for board members starting in January. A listing would have gone out probably about a week or so ago, announcing 3 vacancies on the board come January. We will vote as a board in November with an announcement go out in December. But until that time, we're accepting applications or interested paperwork from interested parties that would like to be on the executive board for GITA. With that, let me introduce Mike Tully and Ben Houston. Mike Tully is the president and CEO of Aerial Services, Inc., located in Iowa, and has been leading ASI for 2 decades. Mike is a certified photogrammetrist and GIS professional. He holds a master's degree in forestry and a master's in business administration. ASI has been performing remote sensing and mapping for 50 years across the nation and has integrated drones in their operations about 8 years ago. So Mike enjoys helping professionals understand remote sensing and mapping, and we're extremely happy and privileged to have Mike on board with us. Ben Houston has over 25 years of experience with mapping technologies ranging from military applications to environmental conservation and public works. Ben is a licensed professional engineer in New York. He has a background in public health engineering, utilities infrastructure, and stormwater management. Ben has worked as both an engineer and a GIS analyst in for-profit and not-for-profit consulting companies with various local government agencies, including county departments of planning, public works, and public health. And like Mike, Ben, we're extremely happy to have you on board here to talk to us about drones. With that, you don't get to listen to me speak anymore. I'm going to turn it over to Mr. Mike Tully, who's going to get us going. So Mike, if you're ready, I'm going to transfer the program over to you and let you take over.
All right, I'm looking for that.
All right, you are now the presenter, sir. Let's see what you got.
Got it.
So just before Mike gets started, this session is being recorded and will be available at gita.org in the Learning Center. And at the end, I think we're going to talk to Ben and Mike about potentially sharing the slides out to those that are interested. And any questions during the session, please refer to the chat window and we will answer all questions at the end of the presentation.
All right, well, thank you, Drew. I trust everybody can see that screen. Does that look good, Drew?
It looks good to me.
All right, good. Well, let's get going. I appreciate Drew for establishing this webinar. My friend and colleague Ben Houston from Ground Point Technologies and I are thrilled to share this information with all of you and hope that everyone will find it beneficial and profitable. As Drew mentioned briefly, ASI has been doing remote sensing and mapping for 50 years now. Using manned aircraft, we provide LiDAR and imagery for many verticals, including oil, gas, transportation, agriculture for private and government clients all over the country. For most of the last 50 years, we've used manned aircraft and large, high-quality, very expensive sensors of different types. We're here today to talk about a really thrilling topic, drones and mapping with drones, and the really scary and humbling concept of positional accuracy. Scary because it's hard. Humbling because, bad things happen even to the most careful professional. Many drone operators today are new. Many are uninformed and some are making exaggerated or uninformed assurances about the positional accuracy of their mapping products. What is positional accuracy and how do you know when you have it with your drone map products? That's what we want to explore today in this seminar. In the last 5 to 7 years or so, ASI has been using drones increasingly and for a variety of mapping projects like dam inspections and modeling, agriculture, transmission lines, things like that. Since the FAA Part 107 rules were released back in August 2016, the commercial UAS data collection is picking up. Although the size of the commercial UAS market under Part 107 is, in my opinion, a mere fraction of what it will become once beyond visual line of sight flying becomes a reality, there are some mapping applications well suited to drones right now. And new applications are being tailored for drones as we talk also. So it goes without question that drones have dramatically lowered the barriers to entry into remote sensing and mapping, and that's a good thing, but it cuts in both ways. Increasing numbers of new remote sensing and mapping practitioners flying these drones are unfamiliar with photogrammetry and other principles of remote sensing and mapping. Some practitioners are still making unfounded, erroneous assumptions about the positional accuracy of their mapping products. So, I like to say that owning a drone is like owning a table saw. Both tools are very capable machines and can create amazing products. But just because you own a table saw doesn't mean you can make a table. And owning a drone does not make anyone a surveyor or a photogrammetrist, and it does not give one the ability to produce survey-grade products simply by owning it. So this session is a discussion about these principles of remote sensing and mapping and how they apply to drones. So let's get on with that. And go to the first principle. I want to talk about 5 principles of remote sensing and mapping. The first is positional accuracy is the final product of detailed planning and diligent work. Accuracy does not just happen. It's hard work, and it's based on principles that do not change. The nature of things, photogrammetry, the science and practice of photogrammetry does not change simply because a new guy is flying a camera up in the sky. Accuracy is not purchased with the drone. It requires skill and careful, informed planning. It requires knowledge about the concepts we're about to go over. And at the end of the day, positional accuracy and quality is a value add that we professionals provide to our clients. Principle number 2, all measurements contain error. We often think, we forget this. Mapping is about measurements, millions of them. Measurements can be good and precise, but all of them contain error. Consider a simple case of a ruler. The most accurate ruler cannot measure distance without some error. This ruler is only good to 1/10 of the unit, maybe 1/20th if you stretch it and interpolate between 2 of the marks. A more accurate ruler exists that can be used to quantify the error of your measurements made with this ruler. Even when we understand this ruler's inherent limit to measurement error, it may still be used ineptly to provide unmerited assurances of accuracy. For example, most of us use ArcMap. Just because ArcMap, or whatever desktop GIS, it doesn't matter, just because it displays values to 1/10,000th of a unit does not mean that number or distance. It could be a GSD, it could be the coordinate position. Doesn't mean that it's accurate to 1/10,000th of a unit. The accuracy of your data is determined by the quality of measurements, not the resolution of your software. The ruler does not convey the accuracy to your data. So just like with the ruler, if I claim that my data is good to 1/10,000th because my GIS says so, then I'm overstating the nature of my data and I'm misusing this ruler without consideration of its inherent limitations to characterize my data. The old adage certainly applies with drones and remote sensing mapping that if you put garbage in, you're going to get garbage out. Just how much error is inherent with your drone systems? Which measurements of position contain the most error? Those are questions we want to get at. The scary thing is that while we're still kind of in the Wild West stage of drone use in remote sensing and mapping, many practitioners don't even know that they're producing garbage and trust that because the ruler or the manufacturer perhaps says the data is good to 2 centimeters or whatever, that their mapping products are inherently that accurate. And I want to assure you that is not necessarily the case. Which brings us to principle number 3, that the entire drone system, everything, the aircraft, the sensors, the operators, the software used to process the data, determines the positional error of the products. It's not just the camera. So it's the entire system. It's important to appreciate that your drone system is making measurements with each observation, and each component of the system is making observations, and each one of those is erroneous. There's some error associated with that. All of this error from all of these components accumulates, and if not managed skillfully, can cause a problem. So the aircraft performance and stability contributes to accuracy of the final product. The pilot skills contribute. The sensors, the quality of the camera, the LiDAR, the GPS chip, the GPS antenna, the inertial measurement unit, all of these components, the flight management system, the type of lens, the image sensor type, whether it's a CCD or CMOS type sensor, each of these things is making measurements and contributes to the total air associated with whatever's falling out of the sky from that drone. I mean, common sense tells us that the best, most accurate drone system in the wrong hands will produce junk, manufacturer assurances aside. So all of these things together are important to the total accuracy of the product. I want to just talk about one example of how one simple thing can have a big impact on accuracy, and that's this rolling shutter. Some of you have heard about it. I'm not going to spend a lot of time on it, but just to use it to illustrate that a lot of drones today are commonly equipped with rolling shutter cameras. This type of camera is inexpensive and it creates great videos. There's a good reason they're so common. But the rolling shutter effect on imagery is prevalent and introduces a new source of air that must be modeled out properly. This serves as a significant obstacle to extracting high accuracy measurements in photogrammetric software unless it is properly managed. Typical DSLR cameras, those that use CCDs as opposed to CMOS, use what's called a global shutter. These are shutters that you and I are most familiar with that open and close and capture an entire frame in an instant. But other cameras, generally these less expensive CMOS cameras that are commonly found in drones, use what's called a rolling shutter. This shutter captures the entire scene in pieces across time. This produces distortions in fast-moving objects, like this helicopter blade that's curved. We know it's not curved, but that's how it's captured with this rolling shutter camera. And most seen in mapping applications, especially when we're flying at less than 400 feet away from features, pretty much everything is always moving quite rapidly. And we have a problem with positioning those pixels captured with the rolling shutter camera. We may not be able to see these distortions in a typical ortho, but they are there and they impact quality and accuracy of all of our products. Pix4D and other processing software that we all use, they do attempt to model out these distortions, but the rolling shutter effect is an added source of air to many camera systems. Drone systems that use global shutters, for example, do not have. They eliminate this source of air. So which type of camera are you using? Do you know? Many don't even know if they're using one or not. Next thing is back to the entire system. This also includes ground control survey, which we're going to talk about here in a minute. The accuracy of your ground control points can have a big impact on the fidelity of accuracy measurements possible. The number and position of ground control points will impact positional accuracy. The processing software that you use to do the aero triangulation, to create point clouds, to do your orthorectification, the skills of the technicians using that software and managing the data files all have a huge impact on the ultimate quality and accuracy of the data, regardless of how accurate the sensors might be natively. Some software makes trade-offs between ease of use and the ability to manage the processes and inherent error. Pix4D, SimActive, Info from OrthoVista, Drone Mapper, all of these things have trade-offs between ease of use and the ability to manage error in all these processes. So just understand what you're using and what compromises are being made, if any, by these softwares. Drone manufacturer claims of accuracy are really limited to just the drone and maybe the package sensor. all the other system components on this slide affect the deliverable accuracy for your project as much or more than the inherent accuracy of the aircraft and sensors. These manufacturer claims really express simply a theoretical maximum accuracy on what could be achieved. So please read the fine print and understand some of these principles. This kind of brings me to the idea of error budget. Basically, a drone system, we like to think of an error budget, that whatever system we're using to do remote sensing, there's an error budget. All these components of a drone system introduce discrete sources of error, and the project normally has some type of accuracy specification or intended use that expresses the client's expectations of accuracy. So the entire drone system's error budget needs to be quantified so you're confident these accuracy specs can be achieved and so you don't exceed your error budget. Unfortunately, today, many of our drone systems, error budgets are unknown. The manned systems that we've been using for decades are well known and have been tested many times. So we know what to expect from these systems. The only way to quantify the cumulative errors of these drone systems that are new, they're changing all the time, different cameras, different lenses, different manufacturers. The only way to know this is to systematically test the positional accuracy of those products. Project specs are important and need to be carefully reviewed to determine if we've got the right tool, the right drone and drone system for the project and are able to meet those accuracy specs for that project. Principle number 4, there is such a thing as accuracy standards, and they're important. Our mapping often must meet some expectation of accuracy. It's up to us to quantify the error in our products created by our drone systems and ensure it is less than some acceptable amount. Much of the work done in remote sensing and mapping is done to meet some type of accuracy standard. But many drone practitioners that I've met, because they're new to the field, they've never made a map before, but now are enabled by this great technology, don't know these standards exist, and more importantly, don't understand how to quantify the accuracy of their data. So some here are familiar with the new ASPRS standards updated a few years ago. That's probably the most common accuracy standard. The USGS have their own standards. We still see the old national map accuracy standards in solicitations used by uninformed clients. These are old, outdated, and are inappropriate for modern data and modern projects. Some people talk about the NSDA, the National Standard for Spatial Data Accuracy, as a standard. It's not a standard. It's often confused with a standard, but it's simply a prescribed method of reporting accuracy statistics that's used and dictated by the accuracy standards. Many clients will use accuracy specs that dictate NSSDA reporting, so it's really good to know what that is. Last, principle 5 is that you must test accuracy to know accuracy or to estimate accuracy. Ground testing is always recommended for mapping, but may not be required for all projects. Your new SenseFly drone, for example, says it can meet a positional accuracy of plus or minus 5 centimeters. I'm just making this up, whatever it says. But because of what we just talked about, how do you know your data from the drone system meets this level of accuracy? As discussed previously, only a portion of the accuracy achieved in your mapping is determined by the aircraft and camera. And in the case, how will you know what the positional accuracy is of your mapping products if you test it? The short answer, you can't. The only way to test is to use checkpoints and ground points. So unless you know from repeated testing of the drone system, the whole system, that it repeatedly and reliably will meet certain positional accuracy, you have to test your data. Or there is an alternative. You could tell your client that it might meet that standard, but that you don't really know. And it's important to understand that these accuracy standards allow that. It's okay to say that. The NSSDA standard allows us to state that we did not test the accuracy, but that it was produced to meet that standard. So manufacturer claims have little to do with achievable accuracy of your product. Don't use manufacturer's tech sheet to quote your capabilities. I understand that it's aggravating to tell your boss that you only meet 10 centimeter with your drone. It shows you from providers claiming, much better accuracy. You need to educate him about achievable, repeatable accuracy, not pie in the sky accuracy. The biggest point of all is control and checkpoints. You never have too much ground control and checkpoints, and typically you cannot professionally afford to eliminate all ground control and checkpoints. If you're going to use these, you need to understand that they have to be 3 times more accurate than the accuracy standard you're trying to meet. It may seem intuitive, but you can't test the accuracy of something without a standard or tool that is inherently more accurate than the thing being tested. So the positional accuracy of ground control points and checkpoints must be surveyed to 3 times more accurate than the required accuracy of your products. So make sure you find a surveyor that understands how to do this and knows what they're doing. All positional accuracy methodologies have limitations, especially when the number of checkpoints is small. I could go into a lot of statistics here, and I'm going to avoid that by just saying that for a statistically valid estimate of accuracy, you have to have at least 20 checkpoints. It's not always feasible, though, to measure 20 checkpoints or ground control points because of fragile terrain, unreachable portions of the project site, personal safety or concerns, or just project budget. Control does add an expense to the project. Complicating this, most drone projects in today's world, where we can only fly them as far as we can see them, cover very small areas, and it's impractical to survey 20 or more checkpoints. So at this point, I'm going to pass the baton to Ben Houston at Ground Point Technologies to discuss more fully ground control and checkpoints for drone mapping. So Ben, here you go.
Awesome. I'm going to wait for the button that says share your screen.
You should have control, Ben.
All right. And get the slideshow going here. A little bit of a delay. There we go. All right, everybody see the slide that says accuracy case study?
Yes, sir.
All right, we got the right presentation. And thanks, Mike, for walking us through the principles. I appreciate it. A quick disclaimer. So Ground Point Technologies is sort of the parent company, and Spatial Analytics is our drone affiliate. So you'll see the Spatial Analytics logo from here on out when we're talking about drones. I was on a conversation just this morning with another drone operator who's flying and mapping, and he said to me, Ben, I can guarantee you that I can fly at a certain height, and I can fly at a certain speed, and I can get the proper overlap, and we can do all the ground control. But I can't guarantee that I can meet, 5 centimeter or 10 centimeter or whatever the accuracy spec is. I don't know how to do that. And I told him, I said, look, Ed, you're in the same boat as everybody else, right? Everybody's learning how to fly, and they're learning how to fly, hopefully the right way. But now we've got to go to the next level and help people learn how to test that data so that they can make some sort of authoritative statement about it in terms of its accuracy. And the principles that Mike just went through are, as he said, fundamental, and they don't change. So what I want to do is walk you through a test case that we did, and here's a sample. This is a farm field out in Western PA, and we used this as a test range. It's actually, there's a little house in the lower left-hand side. It's some undulating terrain. It's not completely flat, but in order to get a statistically valid test of any drone flight, you need at least 20 checkpoints. That any greater than 20. So more than 20 checkpoints to check against the data independently from any control or anything like that you use. And in addition to that, they need to be distributed in some way. There's guidelines on this in the ASPRS 2014 standards that Mike referred to, as well as the NSSDA. So you don't cluster your points. They have to be at least 20% of those points distributed in each of the 4 quadrants as you break your project site up. And there's some rules about how close they can be. If the points are too close together, then they're effectively measuring the same thing, so they need to be spread apart by at least sort of, the rule of thumb is 10% of the distance of the longest axis of your project site. So you have to apply some of these rules when testing your data to make sure that your test is valid spatially, as well as just having the proper number of sample points. So we did that. We wanted to have an ASPRS standard test site that we could fly. We could fly it in different ways, and we could test the results against known quality checkpoints. So a quick reminder about error. So RMSD is a term that we use a lot when we're talking about error. And RMSD is not just the average of the error. If you subtract the value that you got from the value that you measured in the field, and you get that delta, that's not what we're talking about. It's actually the root of the mean of the squares of all of the error put together, which is why you need a sample size of n greater than 20 to get a valid statistical number for the RMSD. So you'll see people talking about, oh, well, I did flight and I checked it with 3 points and it came out good. Right? It doesn't work that way. You have to have to be a valid test. Not only do you have to have 20 points, but they have to be distributed appropriately across your project site, et cetera, et cetera. So there's specific standards that exist that guide you through the process. You don't have to make it up. Another thing I just threw up on the screen for everybody to keep in mind, right? When we talk about accuracy, the 10 centimeter accuracy class, which is now the terminology put forth under the latest ASPRS standards. The 10 centimeters corresponds to about 0.33 feet. When you talk to surveyors or even most mappers, they're talking in terms of feet. Oh, I want a tenth, I want 2 tenths, 3 tenths, right? So how does that translate to these accuracy classes? So the old national map accuracy standards that Mike correctly said, we kind of just need to throw them out. But people still use them. They still talk about 2-foot contours and 1-foot contours and 6-inch contours, and that's fine. We can keep using those terms, but we have to back our way into what that means. So the 10 centimeter accuracy class under the current standards corresponds to equivalent 1-foot contour standard. And so keep that in mind as we move forward, the 10 centimeter accuracy class and the 5 centimeter accuracy class, and jot this number down because we're going to come back to it later. So this number is the RMSD accuracy if we were going to test a topographic product to see whether or not it meets the equivalent of can I make 6-inch contours? Right? Is it good enough for 6-inch contours? That's where we're headed. Now, based on what Mike said, quick quiz, if we're going to test a 5 centimeter accuracy product, what do we need to use as checkpoints? Now, if we're going to use checkpoints, they have to be 3 times better. That's the rule. So if we're collecting 2 centimeter accuracy points with our GPS unit, is that good enough? Well, 2 times 3 is 6. It's getting us close, right? We're in the range, right? So maybe that's close enough for practical use. I would be more than happy to use 2 centimeter checkpoints if everybody was doing it, right? But the fact that nobody's doing it, let's at least start doing it. So if you can get better than 2 centimeter accuracy measured points in the field, right? If it's better than 2 centimeter accuracy times 3, that gets us in the realm of checkpoints that we can use to test for 6-inch contour accuracy. So there's my soapbox about RMSD. All right, so here's our project again. So the first thing we did is let's just fly it with we flew it with a Phantom 4, and then we flew it with an Inspire 2 with the X4S camera. So we're going to talk about the Inspire 2 with the X4S camera. The hardware is really not that significant as long as you're using a global shutter, not a rolling shutter. Then everything works pretty well. So it should apply generically. It doesn't matter what platform or what camera we're using to apply the standards. So the first thing we did is, what do I need control for? Do I have to use control? I don't want to use control. Let's just see what the results look like if we just fly it. No control at all, right? That's what everybody would love to do, because nobody really wants to do control, especially people that don't come from a mapping background. And this is kind of what we're getting out of the can. 7-foot error, which shouldn't be too surprising. It's actually pretty good, given that the DJI platforms do a pretty terrible job of measuring altitude. And we're talking about a cell phone grade stock GPS, that are probably plus or minus a couple of meters at its very best day. Maybe even up to 5 meters in the vertical, right? For a cell phone grade GPS, hey, we're looking pretty good. Right, so this is kind of what you'd expect if you didn't use any ground control or any specific enhancements to post-processing. So I would posit to the group that is unacceptable for most mapping applications. If you just want to take pretty pictures, and maybe for 80% of your drone work, pretty pictures is good enough, then hey, if it's good enough, run with it. But for as a mapper and an engineer, that's not good enough. So we got to figure out what we can do better. So we can use traditional ground control. Traditional ground control requires us to go out and lay targets and measure independently those points, and then use them in post-processing to anchor the project to the ground. And then we'll use our independent checkpoints to validate that. So in this case, we took all of our points. We took saved 20 out to use as our independent checks, and we used 14 as GCPs. So our ground control points. That's what we talk about, GCPs. And we're getting, now we're getting results that look like there's something a little more useful. We're almost in the 10 centimeter range, right? 0.35 feet. Not quite good enough for 1-foot contours, but probably depending on the site. And that's the thing about using traditional ground control. Every site's different. Every site has different topography, has different veg, has different buildings, and has a different geometry. So how you do the ground control has to be customized to each site. And there are probably ways we can drive that RMSD down a little bit and get better accuracies with using traditional ground control. I have a surveyor colleague down in Beacon, New York, who's using traditional GCP approaches with his Phantom 4 Pro, and he's consistently getting in the 0.2 range, right, or even under 0.2. So he's really happy with that, just using traditional ground control. But he's a surveyor, right? So he's got all the gear, he's out there, he's happy to collect 30 or 40 points on every project that he does. Not everybody can do that. Here's a shout out to our colleagues at Wolfpart. Mike and I actually were recently at a conference where Wolfpart was presenting some results, and they did some scenario testing on GCP control. So if you have no control, if you have 4 GCPs in the corners, if we have 4 GCPs in the corners plus 1 in the middle, that would be 5, etc. So you can see these 6 different options. They just went through it methodically and said, if we add control one at a time, how does that affect our results? And it was interesting that as you see the slide, the one in the lower right with the 14 GCPs, actually the error started to go up. So more control isn't necessarily better. sometimes there's a sort of a magic sweet spot. And in their instance, for the test site that they did, that sweet spot was right around 7 control points. And you can see the distribution and how they spread them out. If you look at the 5 GCP in the corner, you'll see that they're still 0.32. That's still within the 10 centimeter accuracy. It was 0.33 to get into the 10 centimeter accuracy range. So even with 5 GCPs, they're able to produce 1 foot contours. So that's, 7 GCPs gives them the best result. And let's see, oh, that's the same slide. There's the photo from Wolfpart of their site that they took. It was their headquarters building with a parking lot and a flat grass. So unless every single project of yours is completely flat with a parking lot and grass, you may have some different challenges with your site. But the point was to test out this idea of how GCPs apply to doing traditional ground control. Now, one of the problems, as Mike pointed out, well, maybe you can't access the whole site. Like, what if I'm doing a wetland project? I can't run control and set targets all over this wetland. What if you're using a construction site that's quite large and you maybe can only get a few access points along the fence? You may not be able to put control everywhere because you may not be able to get everywhere. And because every site's different with topography and geometry, sometimes you have difficulty just using control, period. And by applying control, you get inconsistent results. So one of the things that we wanted to test, I'm going to walk you through now, is if we were to add on a little piece of technology called Postprocess kinematic, PPK, right? It's basically PPK is a piece of technology you can buy, a little piece of hardware. You bolt it onto the outside of your drone, and it does 2 things for you. It gives you a high precision GPS. So you're getting a much better GPS grade signal than you would from the stock cell phone GPS that's in your drone. And it connects directly into the controller on the drone so that it is measuring the exact exposure point of the image, because GPS fundamentally is a time sensitive, you're getting a signal every second or something along those lines. So it measures the exact mid-exposure point of the image to get you much better positional information on every image center. And as a result of using PPK, you can get higher accuracy information directly off your drone. Now, the question is, do we still need ground control to do that? So we were testing that against the manufacturer claims that you can use PPK with no ground control. So that's the claim, and I'll talk about that in a second. So we took our stock Inspire 2 with the X4S camera, bolted on the PPK onto the outside of the device, and ran it according to the manufacturer's instructions and how they all told you how to do it. And so 2 scenarios I want to show you here. Here's the 3-point method. So here's where, if you're taking off right next to the house in the lower left-hand corner, you can use your landing pad as one of the control points. And if you just took a little Frisbee and threw it out to the left and to the right and created a little isosceles sort of triangle-ish, about 20 feet apart, created a little set of 3 points where you could anchor your control down, then you can get results. We tested that on our range against all the independent checkpoints, and we were getting results down inside the 10 centimeter, below 8 centimeters, so 0.28. So we're with 3 control points right next to each other, we're able to get results that are well within 1 foot contour capabilities. And I thought that was pretty interesting. So the next piece of this, before I go on to the next slide, is we said, well, what if I don't own an independent GPS unit? Do I really have to rent a GPS unit or rent or buy one in order to do ground control? Do I have to hire a surveyor every single time? And so the test was, well, what if we just put targets down and we set the drone with the high precision PPK GPS on it on top of the target and triggered the camera event on the drone so that it would measure that target position. So if we use the drone as our ground control measurement device on the ground, just set it on the target, trigger, set it on the target, trigger, do that 3 times right there, right around our takeoff and landing spot, that is sufficient to get the results that we're showing on the screen today. So that's huge, right? Now we can fly highly accurate data without necessarily having to put control all over the whole site. We may not be able to access the whole site. We can do it with 3 ground control points right next to where we're flying, which should be relatively reasonable. We can do that probably in the car park area wherever our truck is where we pulled the drone off. And we don't need an independent GPS unit to do it. We can use the PPK device that we bought to attach onto the drone and just use the drone. So that was pretty significant results. Then we tested what we call the enhanced 3-point method to say, all right, well, if we take those 3 points and we spread them out across the project site, how's that going to change our results? Because the project sites, this one in particular has some elevation change, it's got some slope, and so it does affect the results. And we found that, remember I told you to remember that number up on the earlier screen, which was 0.16. So we're getting down, and we're actually under the 5-centimeter accuracy class. So we're down in the range of 6-inch contours now. So just by spreading the 3 points across the project site without an independent GPS unit, using the drone with the PPK add-on, mind you, we can produce data that's down into that 5-centimeter accuracy class, or as the old adage is, 6-inch contours. We can produce 6-inch contours. So I thought that was pretty neat findings to share with everybody. There we go. Oops. There we go. Getting to the end here. So I had a couple of additional issues to consider. All right. One is that when we're using control or checkpoints, both, targets are not made equal. Now, if everybody could take a second here and look down at your hands. If you look at your forefinger, doesn't matter if it's your right hand or your left hand, you look at your forefinger, from the tip of your forefinger down past the first knuckle to the second knuckle. Now, obviously, we all have slightly different sized hands, but that distance from the tip of your forefinger to the second knuckle is about 5 centimeters. You can measure it on your own later, but that's about 5 centimeters. And so we need to be able to locate the center of the measurement point on the GCP in our imagery. So when we give the imagery back, if we get 1 centimeter imagery or 2 centimeter imagery back, 1-inch imagery, about 2 centimeters, and we are trying to locate the center of that target, and we're off by even 1 pixel, we've just added some error just by not having targets. So if you spray paint targets in an X, or if you're using, say, parking lot lines or something like that, and it gets a little fuzzy in the imagery, and your imagery's 2 centimeter imagery, and you're off by 2 pixels, then you are introducing error. So taking care and using a really good vanishing point target that allows you to see the measurement point within 1 pixel, so you know you're on the same pixel in which the measurement was made, is critical to reducing your error. Otherwise, you're just adding to your error budget. You're adding to your error budget just with the targets, right? Just the targets alone, right? You can do everything completely perfectly and blow your error budget just on your targets. So not all targets are made equal. Another point, and this comes back around to the manufacturer of the PPK devices. One of the things that they recommend is that you calibrate your camera. All cameras, especially the smaller, lower end cameras that are not metric cameras, are going to have some float from, in their internal mechanisms with the focal lengths and how all the pieces got put together in the factory, right? They're not all exactly the same. They're just slightly different. And when these cameras are really small and you're dealing with distances that we're talking about, those really, really, really small differences between cameras, you get the 2 exact same camera type, they're going to have different calibrations. So if you just let Pix4D or Agisoft just sort of run with whatever generic solution that it does when you hit next, finish, you're not going to get as good of results as if you calibrate the camera and then you insert into your post-processing the camera calibration parameters, and then recalibrate your camera every 6 months to a year just to see if those parameters have changed, because they will. You will get different results every time you calibrate your camera over time. especially if you are jostling it in a box in the back of the truck, or you're exposing it to extreme heat or cold. Things are going to move a little bit. They're going to expand and contract and bounce around. And so roughly every 6 months to a year, it's a good idea to recalibrate your camera. And so the manufacturers are saying if you actually use a calibrated camera, now remember our example, we didn't use a calibrated camera. We just used stock camera right out of the box, non-calibrated, let Pix4D do its thing. And we got the results that I just showed you. They're saying that if you use a calibrated camera, you can eliminate ground control altogether. That's our next round of testing that we're going to do. So stay tuned. When we come back around for another webinar, we'll give you the results of the camera calibration and ground control and see how those compare. 2 more points. 1, you can still produce crappy data with really expensive equipment. So we were producing really good drone data back with Phantom 2s before all of the fancy stuff that is all integrated now. It's about, as Mike said, following a diligent process, right? Doing the diligent planning and having some expertise in the full entire life cycle. So you can't just expect to buy an expensive piece of equipment, take it out, fly it, and then hit next, finish on your software and get good results. So you can buy a $60,000 drone system and still wonder why your data is not any good. And then my final comment to everybody today is going back to Mike's comments, and you might want to re-watch the webinar, but understanding principle number 3 is really going to be the key to your success. And for those of you who are paying attention, principle number 3 is the system contributes to the entire error budget, right? You've got a camera error, you've got GPS error, you've got target error, like I just talked about, you've got human error, overlap, lenses, everything. There's a laundry list of stuff that contributes to error. And understanding that and managing that is going to be the key to you being able to produce high quality data. So with that, I've brought us, I think, to the end, and we'll leave this slide up for as long as anybody wants to. And Drew, I'm going to kick it back over to you. Say thanks to everybody for the opportunity to come and talk to you about this stuff. And I know Mike would be more than happy to engage anybody offline if you have questions, as would I. But certainly we're around here for as long as anybody wants to stick around for any questions on the chat window.
Perfect, man. That was awesome, both from Ben and Mike. A lot of information for everybody to consume. We do have some questions, but man, I feel like my brain needs a break from just listening to that. So we've got a question on, Ben, this kind of goes back to your 0.16 foot accuracy. It says under 5 centimeters, but above the 0.16 foot accuracy with a question mark. I don't understand the question, but I can just read them as they come.
That was probably a rounding error. Because I have 2 slides that were sort of probably inconsistent there. If you get your phone out and just do the unit conversion app, right, and just punch in 5 centimeters, right, see what it spits back at you. But I think that was just a rounding error. But yeah, the results that we were getting with the 3-point method were under 5 centimeters. That was the first time we were able to, in any system or configuration of ground control, PPK, non-PPK, we were actually able to produce results that were less than 5 centimeters RMSD. So apologize. I noticed that too right before we went live, that those 2 slides had a slight discrepancy in the numbers, but I think that's what the person was referring to. I
got you. All right, well, perfect. Thank you for clearing that up. And then I've got 2 questions related to the PPK add-on. One
Sure.
is, what PPK add-on were you using on the Inspire? And then I'm curious to know what the cost is for that add-on.
Sure, I can speak to that a little bit. And this would be a kind of a plug for some colleagues of Mike and I that we've known for a long time. There are a number of different sources that you can get PPK technology from. So that's the disclaimer, right? I know there's actually a good company out of Australia called Cloud Geomatics. They make a system, but they're in Australia, so supply management is a bit of a challenge there, but they have a good system. The system that we use is from a company out of Alabama called GeoQ. GeoQ has a subsidiary, just like I talked about with spatial analytics. They have a subsidiary called Ergon, and Ergon makes a PPK unit. And these guys are professional mappers. They've been in photogrammetry mapping for their whole entire careers as well, and so they know what they're doing. So we bought a Loki unit, L-O-K-I, a Loki unit from Ergon, and we're using that on our Inspire system. The cost for that, Drew, coming back to you, it does range a little bit. So I'm going to give you ballpark numbers because I don't have a sales sheet for Ergon, but it's going to be around the $6 to $7 grand add-on, which sounds kind of steep if you just spend $1,500 on a drone, right? You're like, wait a minute, I spent $1,500 on a drone. Why do I want to spend 6 or 7 grand on an add-on? Well, if you consider the cost of GPS and ground control and the cost of bad data, really, that's probably more importantly. What's the cost of bad data over 2-3 projects? If you have to go refly, if you collect more ground control, and if you have a client that's dissatisfied, what's the cost of a client that comes back versus leaves after your first flight? So those, when you think of it in those terms, 5 or 6 or 7 grand is not a big number, but it is obviously a big number when compared to a $1,500 drone package. But you can take a $1,500 prosumer grade drone package, which is an Inspire 2 with an X4S camera, and you can bolt on a piece of technology that might cost more, but you bolt on that technology and now you've got a precision mapping tool that can produce data in the 5 centimeter accuracy range. And I think that story is huge.
Right. Now, since we're talking about add-ons, do you prefer, I've seen some of the new DJI products come out with RTK add-ons already on them. So is there any benefit to going RTK versus PPK? Do I just sound like I'm throwing out letters?
Right. I'll take a first stab at that and then let Mike speak to it, because I think Mike has more life experience with RTK, but this would be my take on that. If you're going to start using RTK, immediately you need to hire a surveyor. Okay. You just should hire a surveyor. You're talking about base station operations. You're talking about live communication between your base station and your rover, and if there any communication link breaks down, RTK, when it works great. It's similar to what I just described with PPK. It's just with a live link. You don't have to post-process in the office. It does it on the fly for you. So you're upping your cost to get RTK, but you're also upping your survey, your level of surveying. And in some cases, even with PPK, I know, like for example, in New York State, you can't do PPK or RTK unless you have a license. But okay. Mike, is there anything you want to add about RTK specifically or PPK?
Well, I'm thinking, not really. I mean, you pretty much covered it. It does take more effort. You do have to set up that base station. The base station on your project site or near, within a few miles of your project site. A lot of states now have these permanent RTK stations that work good for using as your base. But then you also do have to post-process the data. So once your drone lands and you download all the imagery or whatever you're collecting, and you've got to run that through some software and post-process it to refine the coordinate position of each one of those photos based on the GPS recorded with the photo on the drone with the better, more accurate positioning from your RTK and base station.
So the short answer is that, yeah, it works. The longer answer is that the easy button is a lot smaller, right? And if at all, it's a little bit higher lift of technology and surveying.
Gotcha.
And one other advantage to PPK is, it is pretty easy, $6,000 pasted onto your drone, but you also, PPK allows you to calculate positions forward and backward in time. So to figure out where the camera was at when the photo was exposed, PPK allows it to interpolate and calculate and triangulate position both forward and backward in time, which is a huge advantage to getting more precise location information about that camera when it exposes the photo.
Okay, cool, good information. Then this goes back to I think related back to the question we first had about the 5 centimeter versus the 0.16 foot. Because where were the error values in the RMSD calculated? Was it from Pix4D quality report? Manually selected GCPs in each image, or was it from a surface point verified from the output surface?
That's an excellent question. So in this particular case, the error was calculated for every checkpoint. The checkpoints were not used in the processing. They were just independent checkpoints that we measured down to sub 2 centimeter accuracy, like 1.5 centimeter accuracy, because we wanted to be able to check 5 centimeter testing. So we independently measured the points and calculated the delta between the surface model at that, the Pix4D result surface model elevation and the measured elevation of the point, and we threw all that into a spreadsheet. So it's sitting in Excel, and then we use the RMSD formulas. There's actually a pretty cool formula if anybody wants it. I can send it to you, right, or you can Google it, that you can chunk right into Excel for calculating RMSD for a range of data. So we calculated that independently. And what we want to do next, which I was hoping to show today, we didn't get to, is to actually show the delta for every point on the map. And when I showed you my map, I just showed you the points, right? There's the point. Ugh. But to actually symbolize the points based on the error for each point. And by doing that, be able to look at the spatial distribution of error. Is there a pattern? Is all the error along the tree line on the south side? Or is all the error clustered, in the middle? Those types of things. And I think by starting to understand the distribution of the error spatially, we can do a better job of reducing it over time. Hopefully that answers the question.
Yep, I think it does. And then, we're butting up against 3 o'clock, but one last question. ASPRS certification of UAS mapping professionals, do you think it should be a requirement to have UAS pilots certified for whatever reason outside of the FAA certification?
Well, I'll give my stab at that. This is not the position of GITA. This is not the position of ASPRS. This is just Ben. I would unequivocally say no. I think the certification requirements for ASPRS certified UAS certification, whatever it's called, are way too high. And I think there are thousands and thousands and thousands of people flying UASs. We need to make sure that they're producing good data. I think having the ASPRS UAS certification is a differentiator. If you have it, you should use it as a selling point to say, hey, we know what we're doing, but I don't think it should be required.
Okay, yeah, I like that. Right, and for those that are listening, these are the opinions of us as individuals, not as an organization or business owners.
Right.
Mike, do you have any comments for that? Yeah, I would say that professionally, for those of us doing remote sensing professionally, commercially, it makes sense to have that ASPRS certification. It certainly is a differentiator and will become more of a differentiator as time goes on for the professional mapping person. So it's just wise and good business to get that. It's not that hard, and it does increase the likelihood that the operator knows what they're doing. Doesn't guarantee it, but it increases that likelihood.
All right, perfect. And with that, I think we're all out of questions. We're at 3:02 p.m. right now, and I want to thank everybody for participating in this webinar. Mike and Ben, amazing information. Thank you so much. For those that would like copies of the slides, can they reach out to you directly for a copy of the presentation?
Yes.
Mike and Ben? Okay.
Sure.
Perfect.
Yep.
And then this webinar has been recorded and will be hosted at gita.org in the Learning Center. Guys, thank you very much for participating, and thanks for those that were listening. And we'll see you next time.
Thank
It's
you.
our pleasure.